Right, well, good morning to those of you on the West Coast. Good afternoon to those of you joining us from the East Coast, and good evening to anyone joining us from Europe or stations further east. And a very warm welcome to you all. Thank you for joining this, the 44th of our regular series of short courses on pumping topics. This one's going to last about 45 minutes, allowing us time for a Q&A session at the end of the presentation. So let me just restart the screen share. Yep, it's working. So here is a listing of all the previous short courses we've run during the last 2 years. We've been holding them actually for 4 years, so there are a lot more than this, but I'm just showing the last 2 years worth here. If you've missed any of them, you can get a copy of the materials from our website. You go to ruhrpumpen.com and follow the link on the menu to RP Short Courses. When you go to ruhrpumpen.com, you get to this screen, and here is the link to RP Short Courses. If you click on that, it takes you to this screen, and you'll see all of the recent courses can be listed. Here are just the latest 4. But you can click on any of them to see the course material and download copies for viewing at your leisure. So today's seminar is going to look at non-destructive examination. We'll look at magnetic particle examination, liquid penetrant, X-ray, and ultrasonic, explaining when they're appropriate for use, how they're carried out, and the benefits and limitations of them all. We'll be holding a Q&A session at the end, so please use the Q&A facility at the bottom of your screen to ask any questions that you may have or make any comments. I'll address those that I can live at the end of the session, and the rest we'll address by mail in the coming days. We are recording this session and we'll make it available to all attendees as a YouTube link, as well as by emailing you a PDF version of the slideshow and of the Q&A summary from both of today's sessions. Well, here we see the main characteristics of the 5 most common NDE processes. We see their limitations and their comparative costs. So liquid penetrant detects surface cracks only. There's no material limitation, and it's the least expensive. Magnetic particle detects mainly surface cracks, but it will take some just below the surface. Material must be magnetic, and it's inexpensive. Ultrasonic detection detects below surface cracks and flaws. No material limitation except it must be fairly smooth, and we're getting a bit pricey now, it's more expensive. And finally, the 2 types of radiography, electronic X-ray and gamma ray isotope. These are very good for below surface cracks, gamma ray being better for thick materials. The cost comparison, it's expensive. And not just expensive, it takes a lot longer. You might turn a pump that would normally be on a 9-month delivery time into a 12-month delivery time. So we're going to look at all of these 5 in the coming slides. So we start with liquid penetrant examination or inspection. What is it for? Well, it's a method of detecting surface cracks or surface problems. How does it work? Well, it's based on the idea of surface tension and capillary action. So thin liquid spread over a crack, the resulting capillary action will draw the liquid into the crack. Then, by removing the excess liquid from the surface, the liquid remaining within the crack can be made more visible by use of a developer. And this will draw the dipenetrant back out of the out of the crack or flaw and allow it to be clearly seen. So what interpretation is required? Well, the length and the shape of the crack is clearly visible. It's right there in front of you. But how it was caused is not. It only detects surface flaw detection. It doesn't show how deep the crack is or how far it extends. So we would need to do excavation grinding of the part to establish the extent of the problem. Well, these are the process steps. Pre-cleaning, you need to remove any dirt, paint, oil, grease, or any loose scales that would cause false indications. You then apply the penetrant to the surface being tested and allow it to stand for 10 to 30 minutes to allow time to soak into any flaws by capillary action. Remove the excess penetrant and then apply the white developer to the sample. And this draws the penetrant from the defects out onto the surface to form a visible indication. Finally, inspection. Take about 10 minutes after you've applied the developer. The inspector can observe the surface for cracks and flaws. And finally, cleaning after the inspection and recording the defects. Got to remember, you're probably going to paint this pump afterwards, so you want to make sure it's nice and clean after the non-destructive examination. So here's a visual representation of what I've just told you. First, the penetrant application. Excess penetrant removal. Application of the developer. And finally, inspection. But here are the primary advantages now. LPE has a high sensitivity to small surface cracks. It can be used on many materials, metallic, non-metallic, magnetic, non-magnetic, conductive, and non-conductive. Important thing is, as long as they are non-absorbent. LPE can cover large areas and large volumes. It can be inspected quickly at low cost. Even complex shaped parts can be easily inspected. The indications are produced directly on the surface of the part and show a visual representation of the cracks. Because we can use aerosol spray cans to apply the dipenetrant and the developer, it makes it very portable and inexpensive. Easy to use, doesn't require excessive training, which makes it very useful for using in pump assembly shops, for example. The disadvantages: only surface breaking defects can be detected. It doesn't see faults that are below the surface. Must be non-porous. Pre-cleaning is critical since paint or contaminants can hide the defects. It doesn't work on a painted piece of metal. You need to remove the paint before using LPE. Surface finish and roughness can affect the inspection sensitivity. Post-cleaning of parts is required, especially if you're going to be welding. But this is equally true of all the non-destructive examination techniques I'll show you today. Need to consider carefully disposal and ventilation, as the materials we're using might be hazardous and flammable. So that's LPE. The next one we'll look at is MPE, magnetic particle examination. So what is it? Well, it detects flaws on the surface or just beneath the surface, which is a slight advantage over liquid penetrant examination, which will only see surface breaking cracks. How does it work? Well, by magnetizing the part being examined. So that means it can only be used on ferromagnetic materials such as steel, iron, or nickel. The magnetic field that is invoked will change at or near a crack or flaw, which can be made visible by the use of iron filings spread over the component. What interpretation? Well, the length and the shape of the crack or flaw is clearly visible. However, some interpretations are required as the crack can be at or near the surface of the thing. You can't see how far it extends below the surface. So therefore, again, further grinding and excavation is needed to see how far the floor extends. So here's what happens. If the piece is free from flaws, the magnetic field lines run within the piece and parallel to each other. If there's a crack at or near the surface, then the magnetic field lines will locally leave the surface and a local leakage field occurs. Magnetic particle examination will detect these surface defects and those occurring just below the surface. The iron filings will gather at this point. Here are the tools to carry out NPE in the field or in the pump workshop. So here is an AC yoke and here a DC yoke being applied across a weld. Laboratories have much larger permanently installed machines for these, but this is typically what will be used in a pump workshop or out in the field. So here are the process steps. Firstly, for dry magnetic particle examination, and we'll look at wet particle examination afterwards. So first, preparing the surface must be free of grease, oil, or other moisture, which could keep particles from moving freely within the magnetic field. You can carry out NPE on a painted surface if the paint is not too thick. It is less sensitive than it would be on bare metal, but it will work. And this is an advantage over LPE, which cannot be used on a painted surface. Next, you apply the magnetizing force, as we showed in the previous slide, and sprinkle thinly the dry metallic particles, the iron filings, on the test area. A thin layer only, and gently blow away the excess. Switch off the magnetizing force, and then inspect for indications. You look to see where the magnetic particles are clustered. Note that in order to see a flaw, the flaw must be transverse to the magnetic flux. In other words, the flow is in this direction, the magnetic field lines, the magnetic flux is in this direction, so it will only detect a crack that is at right angles to the direction of the magnetic field. So this means that cracks and flaws that are in line with the magnetic flux won't be detected. So what you'd have to do is do a second test in the other direction. So here we have the magnetic field running from right to left. We'd have to do one running from top to bottom in order to see the other cracks and flaws in the other direction. It's then essential that we carry out demagnetization before repeating this test at 90 degrees, or for moving on to the next process in production. I'll cover demagnetization in a few slides' time. The wet particle NPE method, we use smaller wet suspension particles in a carrier liquid rather than the dry particle NPE. Wet particles are smaller than the dry particles, the iron filings. So the advantages that wet particle has over dry particle NPE: you can quickly spray a uniform layer of particles over the entire surface of the component, even large areas. The liquid carrier allows the small wet particles to float into small cracks, so it's considered better than dry particles for detecting very small cracks on smooth surfaces. And it comes in two types, fluorescent and non-fluorescent. The fluorescent ones will glow in the dark when exposed to ultraviolet light, making it easier to detect surface faults in the component. And we'll show that in a few slides' time. So these are the process steps for the wet particle NPE method. It's a little different from the dry particle. First is the same, preparing the surface of the part. It must be free from grease, oil, and moisture. Thin layer of paint will be okay. Then we apply the liquid carrier. And this time it's before the magnetizing field is applied to the component. The suspension of wet magnetic particles is gently sprayed or flowed over the surface of the part. Then we apply the magnetizing force. It's applied in 2 or 3 short bursts, 2-second bursts. The resulting kinetic energy makes the wet particles overcome surface tension and viscosity and allows them to flow over the component and into any flaws that should be there. Then we inspect for indications. We look for the areas where the wet magnetic particles are combined. Surface cracks will produce sharp indication lines. Subsurface cracks will be less obvious, especially if the crack is deeply below the surface. Again, the magnetic flux must be transverse to the floor. In other words, the floor must be at right angles to the magnetic flux. If they're in line, they won't be detected. So then we need to do a second test at right angles to the first one. We terminate the magnetizing force and then demagnetize the tested component. This is very important. It's critically important. If magnetization is left in the component, then firstly, if welding is going to be performed, you can create a condition called arc blow, which can cause the welding arc to be deflected and the molten filler metal may be repelled from the weld. Secondly, any machining could result in metal turnings being magnetized to the component. The magnetized component could cause interference with electronic equipment. For example, if you're going to use proximeters, eddy current vibration probes, they would be interfered with by the magnetic field. Assembly with other components could be made more difficult by magnetic attraction between components, and it could also cause abrasive particles to cling to bearings or wear surfaces. So this is how you demagnetize. It can be done with the same yoke that we used to magnetize it, and what we do is energize it and then pull it away vertically away from the test specimen. And you might have to do this 3 or 4 times. You do a residual magnetism check using a Gauss meter to check that the demagnetization and that there's no residual magnetism left. So you'd apply it, check the whole of the area around where you've done the magnetization. A laboratory will have demagnetizing machines like this one. You pass the component through the tunnel. You can also heat the specimen above its Curie temperature or continuously apply a reversing magnetic field that gradually reduces the magnetic strength. There are other ways of demagnetizing. So this slide illustrates how the fault will not be visible if it's in the same direction as the magnetic field. So here we have the current going from left to right. So we have the magnetic field vertically. So the longitudinal crack will show. This diagonal crack will show. Irregular cracks may show, but this transverse crack will not show. What we have to do is demagnetize and remagnetize with the current going in top to bottom so that the magnetic flux is in this direction along the shaft here. And then this transverse crack is now become a longitudinal crack as far as the analysis is concerned. So here's some examples of dry magnetic particle indications on a saw blade, in a weld, at a fastener hole. I particularly like this one emanating from a hole. If you look at this left-hand picture, you can just about see the crack, but it's very clear once you've applied magnetic particle examination to it. Now some wet magnetic particle indications. Here we see on a drive shaft, you can see the cracks there and there glowing under UV light. Here in a bearing. Here in a crane hook. And here's several sharp radii corners, which ideally would have been radius when it was machined, but obviously on this one they are right angles, and so that's a stress razor and cracks have occurred. Here in a casting, and again in a fastener hole. So that's the first two out of the way. Now we move on to ultrasonic examination, UTE. What is it for? Well, it detects below surface cracks. How does it work? It works by bouncing a high frequency sound wave off any subsurface discontinuity. Any crack or faults within the component will cause a change in the reflection of this ultrasonic signal, which shows up on the diagnostic machine. And the signal reflection and strength can be used to determine the depth, size, and shape of the crack or the fault. It does take a lot of skill and training. Pump suppliers will seldom have this expertise in-house. They'll usually bring in a specialist contractor or send the part to be examined to a laboratory. There are two modes of operation: a reflection and attenuation. First of all, we'll look at the reflection technique, which uses a single transducer as both sender and receiver. So here's the transducer. It's sending out a signal which is bouncing off the back face of the sample back to the receiver. And here again, this time there's a crack in the way, so it's bouncing off the crack back, and it'll tell us how big and where that crack is. So for this method, A liquid couplant, such as oil, is used on the surface of the part where the transducer is located. Purpose is to ensure you've got a good clean signal going through. The reflected ultrasound comes from the back wall of the component, or from a crack or fault within the component, or indeed from variation in density, from porosity. The diagnostic machine displays these results in the form of a signal with an amplitude representing the strength of the reflected signal. The depth of the crack or fault is determined by the arrival time of the ultrasonic reflection. And that's the joy of UTE. You get to see how deep within the component is the flaw. You don't get that with LPE or MPE or even RXE. Now, the attenuation technique uses two probes, a transmitter and a receiver. So the transmitter sends the ultrasound through one surface and a separate receiver detects the amount that has reached it on the opposite surface after traveling through the component. So this time we need to put liquid couplant on both surfaces. Cracks or faults in the space between the probes allow the depth of the cracks and faults to be detected. So here's an example of an illustration of the reflection technique. So the transducer moves along the surface of the component, and when it finds a flaw, a void, or fault, it reflects back, and here's that signal, and bouncing off the back side of the sample is this normal signal. So that's a reflection off the back wall, and there's the reflection off the floor. Here's another example showing the bounce off a crack and the normal bounce off the back surface. Now with the two probe attenuation technique, we can see here the reflection off the back face, and in position 2 here we see it's hit a flaw here, and that's reflected in position 2 here, and here is the back face there. So these are the process steps which apply to both the ultrasonic methods. First, it should be clean, free of grease, oil, or moisture. It should be dry, and any loose dirt, paint, rust, or scale must be removed. It should then be coated with a couplant liquid, such as oil, can be water, which ensures that the ultrasonic signal passes efficiently from the probes to the component. You don't want an air gap between the two. If we're using the reflective technique, then only one surface needs couplant. If the attenuation technique is used, then both surfaces need to be coated. The display machine will show the plot of the signal reflection as we just showed. The most obvious cracks detected are those that are 90 degrees to the plane of the ultrasonic beam, because they stretch across the path of the ultrasonic beam. If it's in line, the signal change may be so weak it may not be detected properly. So sometimes we'll use angled ultrasonic shots, where we angle the probe at 60 degrees to the plane of the component being tested. Like this, we're looking at a weld here, examining a weld. So here's the signals being sent in at 60 degrees, bounces off the back face, bounces off the weld back to the transducer. And here's another example of an angled shot. We're looking at a weld again here, and we see there is a lack of fusion there, which is detected by the beam bouncing off the backside of the sample, bounces off the floor back to the transducer. Showed up there. Next stage, as usual, it's cleanup. Here are the advantages of ultrasonic. 7 points showing the advantages. Has a high penetrating power, which allows detection of cracks and flaws that are quite deep in the component. Highly sensitive, permitting the detection of extremely small cracks and flaws. You only need one surface to be accessible, although you do get better results with the 2-probe attenuation method. But you can do good results with one surface. It has greater accuracy than other non-destructive methods in determining the depth of internal flaws. It'll also detect the thickness of components that have parallel surfaces. Ability to assess the size, orientation, shape, and nature of cracks and flaws. It's non-hazardous to nearby personnel, unlike X-ray, where we're handling radioactive materials. And ultrasonic testing has no effect on the equipment and materials in the vicinity, unlike mag particle examination. It's also very portable and can be automated. The disadvantages requires a lot of understanding and skill and training, which pump suppliers will seldom have this expertise in-house. They'll usually bring in a specialist contractor or send the part to be examined in a laboratory. Components that are rough, irregular in shape, very small or thin, or are not solid, these are difficult to inspect using ultrasonic techniques. They must be prepared by cleaning, removing loose scale and paint. Thin layers of paint are, again, okay, but avoid any loose scale and loose paint. That's UTE. The next one we'll be looking at is radiographic examination. I'm just going to have a slurp of tea. So radiographic examination, RXE. What is it for? It detects below surface cracks and defects. Again, it takes a lot of skill and training. How does it work? 2 methods. Electronically produced X-rays by an X-ray generator. That's a bit like the X-ray generator at your dentist's. And the more powerful one is with gamma rays issued by a radioactive isotope, which is better for very thick and heavy metal components. Both of them, in both cases, we are targeting the X-rays to pass through the part to be inspected. A photographic film is placed on the other side of the part, ready to be affected by the X-rays and gamma rays after they've passed through the part being inspected. The film is developed and then interpretation carried out using a viewer, which requires skills, training to evaluate the dark shadows that appear. Flaws and cracks are seen as negative shadows on the film after it's exposed and developed. So here are the 2 methods. The first one, X-ray generation method. Cathode ray tube contains a small filament similar to a light bulb. The electric current passing through the filament heats up and causes electrons to be stripped off. The high voltage across this gap causes the electron cloud to be pulled towards the target anode, which is usually made of tungsten. The anode has an angled surface so that when the electrons impact on the anode, the impact causes X-rays being generated from the anode in the reflected direction of the angled surface, so down in this case, through the part being X-rayed and impinging on the film. The other method is the gamma ray method. Gamma rays are produced by man-made radioactive isotopes. The isotope is stored in a heavily lead-shielded container for safe use. The user winds the drive cable, which pushes the radioactive isotope through the source cable into the collimator. Here, the collimator, which is where the gamma rays pass through the part, shown here in red, and cause an image to be shown on the film, shown in green here. So the radiographic film is coated with silver bromide. Once it's exposed and developed in a darkroom, the silver bromide turns to black metallic silver, which forms the image as shown here. Image quality indicators, these are required to they're also known as penetrometers and comparators, and they are usually placed on or next to the part being examined. They act as a frame of reference to analyze the samples. They're of known size and penetrability, which helps the inspector to analyze and the indications that he sees. So here are some examples of faults detected in radiographed castings. Here we're seeing porosity, and here shrinkage and hot tears. The advantages of using radiographic NDE: they detect faults below the surface components, even if they're very thick. Minimal surface preparation is required. Nothing is invisible. Most areas can be examined. There are no limitations on materials, except lead, obviously. And you get a permanent record of the inspection with the developed films, which can be kept in the pump record book. Disadvantages: well, it's a relatively high cost and it can take much time. I think I've said before, most pump companies don't have foundries which have the ability to do this sort of work, which means you're going to the to premium foundries to get this work done, which will mean high price and long lead time. A lot of specialized skills required, safeguards to be taken to minimize the danger. You're dealing with radioactive substances here. You need access to both sides of the part. So we've now looked at all 5 of the NDE procedures that we needed to cover. But the question we want to ask now is, what does API 610 require? Which boxes do you need to check on that on that data sheet? Well, here is table 14 from API 610, and it gives you 3 classes of inspection: 1, 2, and 3, 1 being minimum and 3 being the highest level of inspection. Class 2 inspection clicks in at 80% MAWP and greater than 200 degrees centigrade. So what does this actually mean? When does class 2 inspection kick in? I had several questions this morning about this, that people aren't clear of what that means. And I can agree, it's not too clever. So I prepared some more slides on this one. The procedures you need to take to decide which class of inspection applies. First, you calculate your required max allowable working pressure from your process conditions, which is shut-off pressure plus 10%, plus the max suction pressure, and you do all these calculations with the max SG of the fluid. So that gives you the process required max allowable working pressure. Next, we check the pump manufacturer's max allowable working pressure for that pump size and type. Now, for nearly all process pumps with 300-pound flanges, so that'll be OH2s and BB2s, this is specified by API 610 as being at least 40 bar. Here you go. Here's the clause where it says it, 6.3.5, gauge pressure rating at least 40 bar. So 40 bar is your max allowable working pressure. 80% of 40 bar is 32 bar. So if the process calculated max allowable working pressure is at or greater than 32 bar, and the temperature is greater than 200 degrees centigrade, then you require class 2 inspection. For bigger pumps, you check with the manufacturer data. Here's an example of a BB3 pump with 900-pound flanges. In this example, we see the pump design pressure, MAWP, is 105 bar. 80% of 105 bar is 84 bar. So in this instance, if the process calculated max allowable working pressure is at or greater than 84 bar, and the temperature is greater than 200 degrees centigrade, then you require class 2 inspection. So class 2 inspection is visual inspection of the casing plus magnetic particle or LPE of critical areas. What are critical areas? Well, that's defined in the footnotes. Here we go, in the footnotes of that table. Critical areas are inlet nozzle locations, outlet nozzle locations, and casing wall thickness changes. Depending on who you talk to and the complexity of the casting, this could be interpreted as being 100% of the casting, perhaps especially if it were a BB3 casing, which is a horizontal split case multi-stage pump. Quite a few changes in wall thickness there. So there are certain places that the customer might well insist on having inspection done. Going back up to this again. So that was MT or PT of critical areas. If it's a fabricated pump, like a VS6 pump, a vertical barrel pump, you've got magnetic particle of the casing and of the nozzle welds. Here are the auxiliary connection welds, the internals, visual only, auxiliary process piping, that's your vents, your drains, your mechanical seal piping. And if it's butt welded, a certain amount of radiography. So that's for class 2 inspection. If it was below that threshold, then class 1 inspection was just visual, pretty much down the line. And at the other end of the spectrum, class 3 inspection comes in with very light hydrocarbons, less than 0.5, so that would be liquefied natural gas, for example. Or if you're greater than 200 degrees centigrade and also less than 0.7 SG, or when you're very hot, greater than 260 degrees centigrade, or in extremely hazardous services, as defined by the client himself. And then we bring in radiography down the line here. Here is table 15 from API 610, which references the standards to which the non-destructive examination should be carried out and the acceptance criteria. It refers to ASME boiler and pressure vessel code, the BPVC, section 5 for the methods, and section 8 for the acceptance criteria. This will tell you when a floor is acceptable or not, how big, how near the surface, etc. We're nearly finished now, even though we're running late. Here is a question I posted on various pump groups on LinkedIn. If a pump casing has a below surface defect that does not reach the surface, either internally or externally, and the pump casing has successfully undergone hydrotest to 1.5 times max allowable working pressure, does the defect matter? I don't know there's a defect, as I've done no NDE other than hydro. The more NDE you do, the more defects you uncover. So is a small defect deep within the casting important? The casting has passed hydrotest, so arguably the casting is sound. Or do you feel it's necessary to excavate and weld up every potential indication? I got quite a few good answers, and I'll show you 2 of them. This first one, particularly good one from Buddy Morris, who was formerly with ITT Gould Pumps and is now a consultant. And he says, in most cases, no. Defect is a relative term. Many castings have some kind of defect, such as inclusions, shrinkage, etc., that will not affect the performance of the casting. I'm also assuming this is a standard commercial grade casting and will meet all applicable specifications. The customer always has the right to purchase additional NDE. There are some materials and configurations of casting where it's more or less impossible to get 100% defect-free casting. Castings do not typically fail with these type of defects. Your foundry personnel and metallurgists are aware of these issues and will work with engineering on the configuration of the casting, along with gating and risers, to eliminate or minimize this. To do extensive NDE on every casting would make the cost prohibitive and extend lead time significantly. Also, to your point, how do you repair an unknown defect? Excellent answer there from Buddy. And here's another answer which I really like by Simon Bradshaw, the usual pump guru that I refer to often. And his answer was, it depends. One thing to keep in mind is that all castings are to a greater or lesser degree a collection of defects held together with metal. I really like that. For non-hazardous service, it doesn't generally matter. The hydrotest has verified that no gross failure will occur, regardless of how many subsurface defects exist, and they will. But for more hazardous service, it could matter, particularly if the defect became exposed due to corrosion, erosion, and then create a leak path in the pressure boundary. And that's exactly why API 610 requires radiographic or ultrasonic testing for hot and hazardous services, +3 inspection. That requirement is specifically to uncover subsurface defects in critical areas. So in corrosive and erosive service, these subsurface defects could become surface defects. So there you have the answer. Well, that pretty much concludes the fun for today, and I hope you found it useful. I just get to advertise the next of the short courses, which is going to be on understanding customer specification requirements. It's going to be on Thursday, the 11th of December, and it's to be the last course of this year. 2 sessions, one at 8 o'clock in the morning and one at 5 o'clock in the evening, my time. So this course it's intended to help the purchaser engineers and pump vendor engineers understand one another better. It'll answer such questions as, what's the difference between an extended warranty and a deferred warranty? Is a vendor clarification to a specification really an exception? Witnessed or observed, what's the difference? And 3-year uninterrupted operation. Is this or should this be an issue for the pump supplier? Spoiler alert, the answer is no. And there'll be many more. So I'm going to leave the meeting open for a little while just to allow you to post in the Q&A box, and I'll endeavour to answer those that I can here and now. And those that need a fuller answer will be answered in a few days. Our marketing team are standing by, and they will be sending you the YouTube recording, which will need a bit of editing before they send it out, I suspect, with the errors that I made earlier. But they will send you the YouTube recording and a PDF of the presentation and of the summarized Q&A from both of today's sessions. If you need a certificate of completion for this short course, marketing@ruhrpumpen.com. And if you have questions, you can send them to me as well, smith@ruhrpumpen.com. So here, as usual, right at the end are 5 or 6 slides showing what we do and what we make. But you can see those at your leisure in the hard copy of this presentation that you get. So I want to get on now with the Q&A. So let me stop the screen share and let's see what questions we've got. We have 11 as far as I can see at the moment. So let's have a look and start at the top. Mohammed Usman says, hi, Simon. Thank you for the nice presentation. Well, even with the mistakes. LPT procedure is done on final machined castings or raw castings? Could be both. You might want to do an initial one on the raw casting and then carry it out again on the finished machined casting. But it's most commonly, it will be done at the foundry, so it's on the raw casting. Rogelio Espinosa, we can see now the PowerPoint. Oh, okay. Just put on presenter mode. Yeah, thank you. I found out after about 5 minutes. And he pointed out you could see the notes. Well, yeah, you're supposed to see those notes. You'll get them in the hard copy. Anonymous attendee has said, how to ultrasonically test rounded surfaces. Yes, I can see the difficulty if it's a very small diameter one. If it's less than the tool, I think you can probably get the right shaped transducers if that's going to be a regular occurrence. Mohammed Usman says, hi, can we do UT on parts having a cavity inside, like the volute casing? Well, yes, because you'll measure you'll be able to detect the first part of the casing, if you like, through till you get to the gap, and then saying, okay, now we stop there and we apply it to the other side of the casing and measure it from the other way. So once you recognize that there is supposed to be a gap there, when you see the gap, you'll say, right, that's the gap that I expected to see. Mohammed Usman again. Hi, in case only one condition for table 14 class 2 is present, like rated pressure is 80% of max allowable working pressure, however, the temperature is less than 200 degrees centigrade, in that case, inspection class 2 will be applicable or not. It would not be applicable. According to API 610, it is one and the other, both together. However, customer might well look at it and say, I still want it. And then they can tick the box and specify it, and the pump vendor will then take that into account and quote accordingly. Mohammed Usman again, also the same question as asked for LPT. Is RT done on raw castings, or can it be done on machined castings also? The answer is yes, it can be done on machined castings also, but it is usually done at the foundry on the raw casting. Once it's got to the factory and been machined, if you want to do radiographic examination again, I don't know why you would, because you would have detected any flaws on your initial radiographic inspection. But if you did want to do it again, um, it would have to be probably have to be sent off to a laboratory to get done. So more delay, more cost. I'm smiling because yet again, James Kennedy has come on and said, "Can I get a martini, please? Shaken, not stirred." Thanks, James. Anonymous attendee said, "What's the beer of choice tonight?" I think we're getting a bit too close to Christmas, are we? uh, Gennady Amuziev, sorry if I've pronounced that wrong. Thank you for sharing this presentation. Very interesting. And the comments from Simon Bradshaw and Buddy Morris were great. I had the pleasure to work with them in the same company. Huh, good, good. Mohammed Usman, also one general question. Can we perform the post-weld heat treatment of the final machine casting like BB3 or BB4 pumps? Yes, if you do any welding on a pump, you will need to do post-weld heat treatment. That's for sure. What will often happen is at the foundry, you'll be doing it's called production welding during if it happens before the final heat treatment, it's called production welding, and it's just part of the normal foundry business. They will look at the casting, they'll do their inspections, they'll grind it and repair it, documenting at every stage, and then they'll do the final heat treatment. After the final heat treatment, when it gets to the pump manufacturer and he starts to machine it, if he were to turn up any indications then which needed welding, um, then um, that would be weld repair and would be documented and carried out at the pump supplier. Oliver Valdez says, for PT to be applied, does API 610 allow also to consider cracking chromium nickel screen or use of fluorescent? Um, you can use, yes, liquid penetrant can be done with fluorescent dyes. I think that's what you were asking there, Oliver. Jamie Hernandez says LP root pass of full penetrating wells. Is that a BPV, API, or customer specification? Sorry, Jamie, I'm not understanding the question. Excuse my thickness. Alexandra Coquia de Souza says, is there a rule about the frequency to execute the essays? Again, I'm afraid I don't understand the question. The tests. Okay, it was a translation, a Google Translate error. Is there a rule about the frequency to execute the tests? Um, you might choose to do LPE. Well, the LPE, for example, will be done in the critical areas, and the MPE likewise in critical areas, which would be considered to be the the gates and the risers of the casting most commonly, or as it said in the table, if there are changes in casing thickness, perhaps on a BB3 pump. Oliver Valadez says, does helium leak testing, is that allowed by API 610? I will pass on that. I've not had to use helium leak testing on a pump. I think it's very specialist. I will speak to one of our product experts and get an answer in the technical in the written answers that I get you these in a few days' time. So it was 19 questions. That's all I've seen at the moment. So unless there's any more, I think we will call it a day. It's 6:05. We're past beer o'clock, so I'll be. I think I'll be having Togham Brewery traditional English ale tonight, I think, is the beer of choice for this evening. So, thank you very much for attending today. I enjoyed presenting it and certainly enjoyed the Q&A. I didn't particularly enjoy when I had a production failure in the middle of the presentation, but hey, what do you do? What can you do? I hope you found it useful. I hope you'll come back and see me on the 11th of December for the next short course. Thanks a lot and bye bye.